Hello and welcome to this gas exchange and charging course by BoostBusters. This course is about unsteady gas dynamics. It's a slightly theoretical part of my course package, um, and it's general in the sense that both two-stroke, four-stroke engines, spark-ignited or compression-ignited engines do have unsteady gas dynamics as a part of the physics, which needs to be understood to be able to understand how the gas exchange is really happening. If we compare a piston internal combustion engine with a gas turbine, the big difference is that a gas turbine is an engine which is not operating in an unsteady fashion. Everything is happening continuously. We have a continuous mass rate of air and exhaust gases, while the piston engine have either ports or valves which are opening and closing all the time. And when there are valves and ports opening and closing, there are also existing pressure ratios or pressure differences. And when a valve open, the pressure situation in the cylinder needs to be transmitted out to the connecting network, both on air side and on exhaust side. This pressure distribution is done by the presence of pressure waves. And especially when we have very long pipes on either the air side or the exhaust side, and the engine is revving high engine speed, the pressure wave propagation and impact on the overall pressure distribution needs to be taken into account. To make it a little bit clearer what I mean with high revving engine and long pipe networks, I will make a firm example of an engine where the pressure wave propagation and the unsteady gas dynamics might not be important to take into consideration. That example would be a compression ignited engine, a diesel engine, which normally have very short individual pipe runners. So both on exhaust side and air side, compression ignited engine have compact manifolds, most of the time turbochargers closely connected to the exhaust side. They are also running at a very low engine speed, which means that the time for doing a valve event will be very long and the pipes are very short. So the pressure waves will have a long time to run up and down the short pipes in order to equalize the pressure. And in such an engine, the pressure wave distribution doesn't have a so strong impact on the gas exchange process. If we move to the other extreme, which will be a high revving four-stroke spark ignited engine, the time for doing a certain valve event will be shorter, and the time spent in the long pipes by the pressure waves will also be shorter. So the pressure waves will not have time to run up and down the pipes in order to equalize the pressure. So independent pressure waves in these pipes for high revving spark ignited engines will have a significant impact on how the volumetric efficiency and gas exchange process in general will behave. We are talking in the gas exchange area about tuned pipes on air or exhaust side. And when we are talking about tuned pipes, we are actually talking about taking the best out of the pressure wave pressure distribution. And therefore, for high output engine, it's important to understand how the pressure waves are behaving. If we move into the subject of pressure waves, the first category of pressure waves you should be aware of is sound waves. And sound waves are generated while I'm talking. They are having very low pressure amplitude, and they are considered to be isentropic and linear. The pressure waves we find in gas exchange system for piston and reciprocating engines are similar to sound waves, but the amplitude is much higher. So we will have special effects related to the amplitude, and those waves are called finite amplitude pressure waves. To understand a little bit more about pressure wave mechanics, we are trying to imagine a situation when an exhaust valve is opening connected to an exhaust pipe. Please have a look on the upper part of this picture. What will happen then is that a compression wave over pressure is transmitted into the exhaust pipe. So the high pressure signal from the cylinder will propagate out in the pipe as a compression wave. The wave itself will have a propagation speed named Cp, and the propagation speed will be the local speed of sound. The local speed of sound in air, kept at about 20 degrees Celsius, is typically 340 meters per second, but in an exhaust pipe, when the exhaust temperature might be some 700 degrees Celsius, the propagation speed, the local speed of sound, is much, much higher. Another thing is that when the amplitude of the wave is no longer neglectable, it's called finite. Both pressure and temperature inside the compression wave is increasing. So the peak segment of the compression wave will actually move faster than the low amplitude parts of the wave. So when the finite pressure wave have been propagating some distance in a pipe, we will have a distortion of the wave. So the front of the wave will be more steep and the tail will be more swallow. If this pipe is long enough, the wave front will become vertical, and then it can shape something called a shock wave. And the shock wave is no longer isentropic wave. It's something much more complicated, and a situation which doesn't occur so regularly in internal combustion engines, and it's actually a non-wanted situation. The pressure wave are interesting as such, but maybe even more interesting is how a certain pressure wave impact the particles in the pipe. The particle is the mass rate. And when a right moving compression wave hits particles, the particles will have a speed gain in the same direction as the compression wave is propagating. And the speed added to the particles is also proportional to the amplitude of the pressure wave. The same picture, I'm not fooling you, but now we should focus on the lower part of the picture. Here we have a situation with a decompression wave. It's an under pressure which is transmitted to the pipe, and we can imagine that we have a cylinder and a valve here, but it's an inlet valve. And we have subatmospheric condition happening in the cylinder because of the piston moving downwards quicker than the inlet valve allows. So we are creating a pressure ratio over the inlet valve. The decompression wave is also a finite pressure wave. finite amplitude pressure wave. But here we have a lower velocity, propagation velocity for the pressure wave at its peak. So when the wave have propagated for a certain time in the pipe, we are actually creating a shock tail on the wave, and the front of the compression wave is becoming swallow. So it's a little bit the mirror image of what's happening on the compression wave. And this is also because the temperature and pressure in the wave is changing and becoming colder, and therefore having a slower propagating velocity here at peak amplitude. The particles experiencing a right moving decompression wave will have a speed, an added speed, so to speak, which is in the opposite direction compared to the propagation direction of the wave. So typically, the particles or the mass rate will move in the opposite direction when they are hit by a pressure wave like this. A pressure wave which is propagating in a pipe with constant area will not change so much. So once it's formed as a compression wave, it might be a little bit distorted, as explained before, but generally no reflection or transmission will happen. But immediately when we have an area change, like in the picture here, where we have an area increase, there will be a pressure wave reflection. If the incident wave is a compression wave like this, coming to an area increase, because of the boundary conditions stating that the superposition pressure in the thin pipe and in the big pipe would be the same, a decompression wave will be generated as a reflected wave back to this end. The remaining part of the compression wave will transmit also as a compression wave, but at a lower amplitude. If the other thing would happen, instead of an area increase, we might have a closed end or a semi-closed end. The wave reflection will be of the same identity as the incident wave. So instead of creating a decompression reflected wave, we will have a reflected compression wave coming back. Transmitted waves in partly closed ends will also be of the same identity as the incident wave. Decompression waves are also changing the identity. So if we have an incident decompression wave, the red one here, reaching an area increase, it will change its identity and reflect back as a compression wave. Part of the incident decompression wave will transmit through the area increase, but transmit further down the system also as a decompression wave. The finite amplitude pressure waves is appreciated in gas exchange systems, since it's possible to give the pipe network geometries which could benefit from the waves. They could be reflected back and support the gas exchange process. If we have pressure waves which are allowed to propagate long enough, or in the case of entering a diffuser, there are a small danger to create a shock wave. And the shock wave is no longer an isentropic wave, and it's always a loss to have it. Because shock waves are just not able to have an impact on the mass rate because they are not able to reach the particles. The last statement before going into some of the applications of finite pressure waves is just a comment that I have deliberately decided not to give you equations stating amplitude levels and how the particle velocity relates to the wave amplitude. If you're interested in this level of detail, I recommend Professor Gordon P. Blair's books for both 2 and 4-stroke engines. And the equations are not that complicated. So if you're interested, please don't hesitate to have a look in his books. One of the most important applications of finite pressure waves in the external gas exchange system could be the exhaust primary pipe cycle in a 4-stroke engine. So imagine the piston and the cylinder and the simplified exhaust valve and the exhaust primary pipe running down to the atmosphere in such an engine. That will be represented by a distance or an coordinate, while the vertical part of the diagram basically is time. But if you decide for a certain engine speed, a time domain could always be transferred to a crank angle event. And the first crank angle event we have here is at 6,000 RPM. And the red beam is the duration of the exhaust valve in a single cylinder 4-stroke engine. The blue one is the inlet valve event, coming a bit later, of course. At time 0, the exhaust valve opens, and to simplify for educational purposes, we assume that the compression wave coming from the high pressure cylinder is instantly transmitted as a kind of point or very, very thin compression wave propagating to the open end, reflecting as a decompression wave, the dotted line, and ideally coming back to the valve overlap, reflecting at a fairly closed end, back to the open end as a decompression wave, and once again changing identity to a compression wave. When the compression wave, which is always bad news at the exhaust side of a 4-stroke engine, comes when the exhaust valve is already closed, it doesn't harm the engine. But imagine a situation at a lower engine speed where all the valve events takes longer time. There is a potential danger at a certain engine speed that the compression wave actually comes back and have the opportunity to hit the engine before the exhaust period is over. And then the tuned exhaust pipe intended to support the engine at 6,000 RPM at 4,000 RPM can do the opposite. Looking at the pressure wave history in the beginning of the exhaust primary pipe, which means very close to the cylinder, this is how the pressure history could look like. And this is the output from a simulation, a 1D engine simulation. The exhaust port opens somewhere here, and all the compression waves we have been looking at will be initiated here. If we look closely, it's not only one pressure trace, it's actually 3. We have a total forward and backwards pressure wave here in the simulation. The total pressure or superposition pressure would be the red one, and that could also be measured by a pressure transducer. What is important to understand in what direction the mass rate of particles will be impacted is the forward and backward running pressure waves. Unfortunately, this information is not available from an experimental results, you need to do simulations in parallel. But having experimental data available, it's possible to calibrate the total pressure trace and calibrate the simulation model, and then doing the drill down in the simulation software to have a better understanding in what direction we are impacting the mass rate of the engine. So this is a very good example why simulation and engine test experiments needs to be done simultaneously to obtain the best possible results. The gas dynamic theories will be also part of the courses more directed to two-stroke and four-stroke engines. And please use this part of the course as a reference to go back to in order to understand phenomena which are covered in other courses. As usual, never hesitate to contact me if you have any further questions at lennart.sander@boostbusters.com. Thank you very much for your kind attention.